On the morning of December 26, 2004, a massive magnitude 9.1 megathrust earthquake ruptured off the western coast of northern Sumatra, Indonesia. The sheer force of the displacement lifted hundreds of miles of ocean floor by dozens of feet, violently pushing thousands of cubic miles of seawater upward. Within minutes, catastrophic waves slammed into the nearby coastlines of Indonesia and Thailand. But what horrified geophysicists was what happened next. Just hours later, that same wave surged ashore in India, Sri Lanka, and eventually as far away as the eastern coast of Africa, thousands of miles across the Indian Ocean. The tsunami had crossed the entire expanse of the open ocean at speeds exceeding 500 miles per hour, matching the cruising velocity of a commercial Boeing 777 passenger jet. Yet, to crew members aboard ships floating in the deep ocean, the wave passed completely unnoticed, appearing as a gentle, imperceptible rise in the sea level of only a few inches. How can a wave carry enough energy to destroy entire coastal cities while traveling at the speed of a jet airliner in deep water, all while remaining virtually invisible to anyone floating directly above it? To understand this incredible physical phenomenon, you have to look at the fundamental differences between standard wind-generated ocean waves and deep ocean tsunamis, because they operate under two completely different sets of fluid dynamics laws. When you stand on a beach and watch standard ocean waves crash onto the sand, you are looking at wind-driven surface waves. These waves are created by friction between blowing air and the uppermost layer of the water column. Wind waves are strictly a surface event. Their energy rarely penetrates more than a few hundred feet down into the water. Most importantly, the speed of a standard wind wave is determined primarily by its wavelength, the distance between two consecutive wave crests. For wind waves, that wavelength is typically a few hundred feet at most. Tsunamis, on the other hand, are not created by wind pushing on the surface. They are generated by a sudden, massive displacement of the entire water column from the ocean floor all the way up to the surface. Whether caused by a submarine earthquake, an underwater landslide, or a volcanic collapse, the entire body of water, from the abyssal plain miles down up to the sunshine layer above, is pushed upward simultaneously. Because a tsunami involves the entire depth of the ocean, it behaves as what fluid dynamics engineers call a shallow water wave. That terminology sounds completely counterintuitive when you are talking about an ocean that is 3 or 4 miles deep. How can a wave sitting on top of a 3-mile-deep abyss be classified as a shallow water wave? In oceanography, a wave is classified as a shallow water wave whenever its wavelength is significantly larger than the depth of the water it is traveling through. Specifically, when the wavelength is more than 20 times greater than the water depth. While a standard wind wave has a wavelength of a couple hundred feet, a deep ocean tsunami possesses an astronomical wavelength. The distance from the crest of a tsunami to the crest of the next wave behind it can stretch anywhere from 50 to over 150 miles long. Compared to a wavelength of 100 miles, an ocean depth of 3 miles is extremely shallow. Because the ratio of water depth to wavelength is so small, the entire ocean column feels the bottom, and the physics governing the wave change completely. For shallow water waves, a fascinating law of physics takes over. The speed of the wave no longer depends on its wavelength or how it was generated. Instead, the speed of a shallow water wave is determined almost entirely by a single variable, the depth of the ocean water it is passing through. The mathematical relationship governing this motion is remarkably simple. The velocity of a tsunami equals the square root of the acceleration due to gravity multiplied by the depth of the ocean floor. Gravity is a constant, which means that as the depth of the ocean increases, the speed of the tsunami increases alongside it in a direct mathematical relationship. In the deep, open trenches of the Pacific or Indian Oceans, where the seabed sits at an average depth of roughly 15,000 feet, that equation yields a mind-boggling result. The wave travels through the deep water at roughly 500 to 550 miles per hour, the exact speed of a commercial jetliner flying at high altitude. Because the wave is moving so exceptionally fast in deep water, its vast kinetic energy is stretched out horizontally across its 100-mile wavelength. Out in the middle of the ocean, a tsunami wave might only measure 1 or 2 feet in height from trough to crest. Because that 2-foot rise is spread out across a distance of 100 miles, the slope of the wave is virtually flat. A ship floating in the deep ocean would gently rise 2 feet over the span of 20 or 30 minutes and then sink back down, with the crew completely unaware that a jet-speed wall of energy just passed beneath their hull. This incredible speed explains why deep-ocean tsunamis pose such a terrifying hazard to distant coastlines. A megathrust earthquake occurring off the coast of Alaska or Chile can send a deep-water tsunami racing across the entire Pacific basin, arriving in Hawaii or Japan in just a matter of hours, giving emergency management agencies a remarkably narrow window to calculate trajectories, issue evacuation orders, and clear coastal zones. However, the physics of a tsunami undergoes a radical, destructive transformation when the fast-moving wave finally reaches the shallow waters near a coastline. As the tsunami approaches a continental shelf, the depth of the ocean floor rapidly decreases, dropping from 15,000 feet down to just a few hundred feet or less. Because the speed of a shallow water wave is governed directly by water depth, the front edge of the tsunami begins to slow down dramatically. It drops from 500 miles per hour to 70 miles per hour, then to 30 miles per hour, and eventually down to the speed of a sprinting human. While the front edge of the wave is grinding to a halt in the shallow coastal waters, the back end of the wave, still sitting miles out in deep water, is still charging forward at 500 miles per hour. This creates a massive fluid traffic jam known as wave shoaling. The vast kinetic energy that was previously stretched out over a 100-mile wavelength in deep water becomes compressed horizontally into a narrow space. Since energy cannot be destroyed, that horizontal compression forces the water upward. The wavelength shrinks dramatically while the amplitude, the height of the wave, soars skyward. The 2-foot bump that slipped silently beneath ships in the deep ocean suddenly compresses into a massive, turbulent wall of water standing tens or even 100 feet high. Furthermore, because a tsunami is an entire displaced water column rather than a surface wave, it does not simply break on the shore and retreat like a normal ocean swell. It surges ashore like an endless, fast-rising tide that keeps pushing inland for 20 to 30 minutes continuously, flooding coastal areas, crushing infrastructure under immense hydraulic pressure, and dragging vast amounts of debris back out to sea when it finally retreats. To track these stealthy, jet-speed waves across the open ocean, scientists developed the DART system, Deep Ocean Assessment and Reporting of Tsunamis. Deployed across the Pacific and Indian Oceans, DART consists of ultra-sensitive pressure sensors anchored directly to the seafloor. These sensors measure the minute weight of the water column above them. When a tsunami passes overhead in deep water, the sensor detects the subtle 2-inch increase in water pressure, transmitting the data via acoustic telemetry to a surface buoy, which instantly beams the information to global warning centers via satellite. By calculating the precise depth profile of the ocean floor along the wave's path, supercomputers running fluid dynamics models can predict the exact arrival time and wave height of a tsunami anywhere in the world, down to the minute. The deep ocean tsunami is a masterclass in planetary physics. It is a wave born from the crushing tectonic forces of the Earth's interior, propelled across vast abyssal plains at the speed of a jet engine by the sheer math of ocean depth, and transformed into a destructive force only when it collides with the shallow shores of the human world. It serves as a stark, humbling reminder that beneath the calm, blue surface of our oceans, kinetic energy can move with invisible, unbelievable speed.